is Kitab, and for Muslim, you can follow your own religious practice. All right. Thank you very much for joining our lectures this morning. And sorry for taking a bit of time before starting our lectures, because just to focus with marking your test. Question number one. Actually, I am the one that set up the question number one for the test one. And I have how many students? Almost 300, 400 students to do the marking. All right, it's okay. That's my duty. So our duty today is to look at the CST. We have look at the theoretical part of the CST. So I just briefly revisit what we have discussed before. So what is CST and how this CST different with other finite elements theory that we have learned in the previous topic. So actually the CST is just the type of elements. We use a different type of elements in modeling our problems, which before we in starting from bar until frame structure, our element is in the form of a straight line, but uh, uh, by using straight lines, element is still possible to determine the what we call it, the displacements, the what we call it, general displacements of your structure. But if you are to look into very detailed distributions of the for example, stress, strain, and also probably you may interested to look into the distributions of the displacement across the cross-sectional area of your structures. Then we may need to extend our analysis in 2D or 3D space, which is in the CST, we just limit our discussions on the two-dimensional continuous structures. But we are living at 3D in a 3D space. Most of the problem that we face or the geometry that we see around us is in 3D, right? So in some cases, we need to solve the problem in 3D. And in some cases, the problem, if the problems, even though it's in 3D, but in some cases, we can reduce the complexity of the analysis into 2D. So CST is just a type of element which is in a triangular shapes. And for one triangle is represent one CST element. And for one triangle, we have 3 nodes. And for one nodes, we have 2 degrees of freedom, which is in the form of both in the form of displacement in the horizontal and vertical deformation or displacement, as represented by the slide as shown on your screen. All right. So we have looked at this. In order to determine the element stiffness metric, then we in the CST finite element approach requires us to do the matrix multiplication as shown in the slide, which is the element stiffness metric for one CST element is actually governed by the thickness of the element itself, the area of the triangles, and then in one triangles we have the element strain displacement metric B, which is, as we can see here in the B metric, it just contains the geometrical informations of the CST itself. If we can remember, y23 is actually referred to y2 minus y3 in the coordinate system. And then we have D metric, which is material metric, which is we must include in the stiffness, element stiffness metric. So for one CST element, then we have to include the material information of that particular CST element. Then we have two choices of setting the material metric, which is whether it is a plane stress conditions or plane strain conditions. And this is must be these two conditions actually depends on the arrangements of the structure itself and also the load that apply to the structures, as we discussed before. So usually I would like to remind again, usually in the test we will explicitly mentions that this structure or that structure that you are going to solve is subjected to the plane stress conditions or plane strain condition. Maybe we tell it, but most of the time, especially during the final exam, or if you go outside, you look at any structures and then there is no such ways that telling you straight away or printed somewhere that that particular structure under the plane stress or plane strain condition. So we as an engineer, we have to be able to evaluate whether that's a kind of the structures and the loads applied to it. So our structures is subjected to the plane stress or plane strain condition. So we have discussed about this in the previous meeting. So actually, in these lectures, which is to demonstrate to you how we could use this, where is it? This kita dah buat ke sebelum ni? Yang ni? Kita buat yang frame kan itu kan?
Buat je sampai cari X. Macam X.
Kita tak buat lagi example yang CST kan?
Tak boleh.
Okay. Alright. Since the approach that presented in your lecture note is require what we call a very lengthy process, but we actually have documents or approach that actually simplified versions of the process for finding the element stiffness metric, which is as shown in the separate document here, which is this document we supply during the test and exam, but it's not directly what we call it. It's not part of the lectures presentation. Okay. All right, now let's we look at this document first. So what do we have in this document? First is we have the T metric, which is actually this T metric is just a transformations metric. Wait, I think this is not the correct one. Sorry. So this is not the correct one for the CST. Give me a second. Okay, this one will be the correct one. Yeah, okay. This is will be the correct one for the CST. That's why I a bit confused just now with the document. It look different. All right, now let's we look at this document. Let me enlarge it a bit here so that you can see clearly what contains in the document. All right. The approach, which is very similar to the one that we processed for the frame structures before. So we know that our K here actually is dA B transpose D multiplied by B. So if you solve this metric multiplications and multiply by the two constant thickness and area, if you work in the symbolic approach, that means you work with a variable, then you multiply all of this. Actually, it will give you this equation here. So as you can see in this K, this K which is we have to solve for every element. If we have 5 elements, so this must be solved for all 5 elements. And the informations in terms of the, we know that the B metric strain displacement is only contains geometrical information, right? Geometrical informations of your triangles or CST, and D, which is your material metric. Say material metric. So if we look at this metric, so we have all of this information. We have D, we have A, we have the D, which is referred to the material information, and then we have the geometry information Y23, X32, in all elements in our matrix. But we have to be careful with this CST, which is in these selections of material. Okay, materials, whether it is for the plane stress or for the plane strain. Usually the value for the modulus of elasticity is obtained from your material analysis, which is you can obtain this E. In the test, we supply the information for you, and then the Poisson ratio of your structure as well. So, all right, now let's look how easy to implement this equation as compared to the one that we have in the slide. But before that, let's revisit here. We have J, which is defined similarly in your lecture notes. So we have J, which is the Jacobian matrix, given by x13, y13, x23, y23. And in order, we use J metric in many places. We use J determinant of J. We use in obtaining the area of the triangles. And also, actually, we use in the strain displacement metric. But this, for the strain displacement metric, is it's already included in this big metric here. But for A, we need to solve the determinants of the J metric, and then we divide it by 2 in order to obtain the area of the CST triangle. So in this case, it doesn't matter how our CST elements looks like. Maybe our CST elements, which is has a perfect angle between the edge. So this is the best triangles to have. But in some cases, when we have a complex geometry, then our mesh, our element may be skewed too much. So when it's skewed, then we may have two angle between the edge of our CST element, which is maybe too small, which make it become very skewed. So a skewed element in finite elements should be avoided. So we should avoid the skewed elements. Because the skewed element actually will provide a large error in the analysis. But in our case, we are going to look at how should we obtain the area of a CST or a triangle of any form by using the determinants of J metric. So we take a cross product, and then we take a half of it, then it should represent the area of our triangle. So this A will be applied there in our K metric, K element metric. So now let's look at this problem. So let's say we have this problem, which is it mentioned there that we have two-dimensional loaded plate shown. Determine the displacement at node 1 and node 2. So let's draw the degrees of freedom at each nodal points. So we have something like that. U4, V4, U3, V3, U1, V1, U2, V2. So this one will be 0, 0, 0, 0. So V1 will be 0. So we need to determine U1, which is at node number 1. We have the pin roller, which allow this particular joints at node number 1 to slide to the left and to the right. So it has degrees of freedom in the horizontal direction. So we need to determine this as well, which is U2 and U3. And it mentions here that the elements stresses using plane stress condition. So it's explicitly mentioned there. Our problem is under plane stress condition, which is, as you can see here, we have the length of the structure, which is 3 inch, 2 inch, and the thickness is just 0.5 inch, which is a kind of thin plate, right? It's kind of a thin plate. So most of the thin plates problems, which is falls under the plane stress condition. Body force may be neglected in comparison to the external forces. So we ignore the body force. All right, now let's look at, okay, now we have two elements. So two elements, which is the element number 1, which is the triangle at the bottom here. So this is element number 1, which is joining 4, 2, and 2 and 1. But we have to remember, we have to order our CST triangle here so that the nodes numbering should be in anti-clockwise direction, so that we will get a positive value of area. If the way we arrange the nodes numbering here, if we choose the arrangements that will make it in the clockwise direction, then you will get negative value of area. So area shouldn't be negative. It's either we have it or we don't have it. So if we have it, we should have a positive area. So the element connectivity is provided here. So let's we take for the element number 1. So the element number 1 is connected from 1, 2, and 4. So from 1, 2, and 4. So it's make the anti-clockwise direction. Actually, I recommend you to try to solve this so that you will have clockwise directions in terms of the nodes arrangement, and then try to check for the what you get the value for J. All right. Now we would like to calculate the K, the element stiffness metric for element number K. So what is K1, and then what is the value for the K2? So the process for obtaining K1 and K2, they are very similar. So in this case, because we have very limited time, so we are not going to solve both of them. So we just try to look at for the K1, and we just choose some element in our K matrix. This is just to prove that the document that we have separately here actually will generate the similar information as if you solve it by following the procedure as shown in the in the lecturer's slide here. All right, let's we look first at our K1. So let me just copy this, and then we put this one next to the K matrix that we have here. All right. So I can make it, I can enlarge it here. So this is what we would like to obtain. And we have calculate this using the solutions as shown in your lecture notes. So let's we try prove this. Since our problem, which is a plane stress problem, so we choose the first equation for the material. So we choose this one for the material properties. And then before that, what we need to do, we need to know our element here, which has, sorry, my drawing is very bad here. So we have 3 inch. And then we have 2 inch height. And then we know that the thickness, which is 0.5 inch. So now let's we prepare our connections just now from 1, 2, and 4. 1, 2, and 4. In terms of the boundary condition, here 0, 0, this one 0. The one that we have is just this, and this. All right, now let's we look at how should we deal with the J matrix. J, which is requires X 1, 3, Y 1, 3, X 2, 3, and Y 2, 3. So can any one of you try to solve this for me, please? Which is in this case, if we look locally, our nodes, we only have 3 nodes, right? 3 nodes for one triangle. So if I write this locally, so this is my node number 1, nodes number 2, and this will be my nodes number 3. So the J matrix is actually written in local. So you have view your triangle in local. So we take x13 equal to x1 minus x3. So taking that this is our origin, which is 0, 0, and then x1. Where is your x1? Your x1 is there, right? So we take this direction is as our y direction, and then that direction is the x direction. X1 is 3, x3 is 0, so we have equal to 3. And then we have y13. So y1 minus y3. y1 is 0. y3 is also 0. So you get 0. Then you have x23. Your x2 is there, which is 3. Minus x3 0. Then you have 3 as well. Then we have y23, which is y2 is 2 minus y of 0.3 here, which is 0. So you have 2. So you plug in here. So your j equal to 3, 0, 3, 2. So we take a cross product. 3 multiplied by 2 equal to 6. Then minus by 3 multiplied by 0. Then we have 0. Then our J matrix is equal to, this is the determinant. The determinant of J is equal to 6. And if for the area, is half of the determinants of the J, which is half of 6, which is we get it equal to 3. So since our structures, the next element which is had the same dimension, so you can say that area for the element number 1, which is equal to the area for the element number 2. So if you write it like this, so we still can accept your answer. So we're done with the calculations of area, which is we need this information in our K matrix there. Can you still can see my the screen guys? All right. Okay, now we're done with the determinations of geometric and area. Now let's we prepare this. Let's we try to prepare the first element, which is the answer should be equal to this one. Okay, provided we choose the correct plane stress equation for the material. So, all right, what is the area? What is the new the Poisson ratio for the structure? Okay, it's mentioned there that the modulus of elasticity, which is 30 times 10 to the power of 6 psi, and then the Poisson ratios equal to 0.225. So this is the Poisson ratio. All right, now, since we have that information, then we straight away plug it into the plane stress equation for variable D11, D22, D12, D21, and D33. So I hope you can help me at this stage in order to obtain this information. So I don't have much space here. Otherwise, if I zoom out, then it will probably hard for you to see the font. So I have to remove some of this. So what you need to do is to prepare D11, D12, D33, because this information will be used in some places within your K matrix. Let's say we just prepare D11 and D33. So we have D11 and D33. Can someone of you try to solve this for me, please? We have 30 times 10 to the power of 6 divided by 1 minus square of 0.25. So this is will give you D11 and D22. Can someone punch the calculator and share the value here, please? All right. So we have 32. So one of your friend sharing the numbers. So I hope the other, we have 46 somethings brain in this groups. So I hope the other 35 will verify the numbers here. If you get some difference value, then maybe either okay, Ali Akila. Okay, Ali Akila has checked. What about D33? Because we need to use D33 here. We just calculate D11 and then we need D33. So D33 is 12 times 10 to the power of 6. All right, now we have this information, D11 and D33. Then we already calculate Y23, which is equal to 2. And then X32, we didn't calculate it yet, right? D32. So we calculate X32, which is equal to X3 minus X2. And this will be X3, which is equal to 0, because this point here is, we take it as an origin. Then X for the point number 2, we have 3. So X32, which is equal to negative 3. So if you plug in this number into this equation, so we have for the first element, so I just write it here, we have 32 times 10 to the power of 6 multiplied by square of 2, and then plus by 12 times 10 to the power of 6, then we have square of negative 3. So if you calculate this, solve this numbers here, this number should actually equivalent to the one that we have on the top here. Can someone of you help me on this? So I hope other than Aiman, Shafiq, Ada Akila, so the rest is the rest are with me in the lecture because I can see you and I can hear your voice. So I assume that all of you are with me now. Abdul Rahim ada? Abdul Rahim, can you calculate this for me please? Dia kena panggil seorang-seorang kot ni baru menonjol. Kalau volunteer, tak ada yang volunteer. Abdul Rahim? Tak ada. Irene Musliha. Cepat. We don't have so much time. We just have... Okay, Saiful. Is it correct, this one? 236 times 10 to the power of 6. Sekejap 236 times 10 to the power of 6. Alright. Can someone of you check? Actually, I have done this so many times before. Cuma yang ni nak you all experience. Actually, we have checked that this document should provide the same result as the 0.25, 0.5. Okay. Now we have for this 3 to 6 times 10 to the power of 6, right? So this should be correct. But for the K, this is for the K, then you have to multiply by T and then divide by 4A. So you know the thickness. So if you multiply your numbers here and then multiply by 0.5, then divide by 4, multiply by 3, right? Our area is 3 just now. So you please don't miss the variable. We have a constant variable outside of our matrix here. Ni yang ni jangan tertinggal ni. Yang tadi kita kira, yang ni je yang kita kira. So kita belum darab lagi dengan yang dekat luar dia tu kan. Alright, so Syafiq 0.983 itu je. Okay. So Syafiq, okay, from the calculations, okay, Shafiq tell us that he got 0.983 times to 10 to the power of 7, which is these numbers actually equivalent to the one that we have from the solution from the lecture slide, right? So this is the the way how we use this document in order to obtain the element stiffness metric, which is this solutions again here. This metric here is a simplified versions of this. The simplified versions of this process here. If you wish to solve this following this step, you still can solve it. You still get the same results, but I think it will take you more than 5 minutes to get the solution for the K just for one element. If you following the approach from me, let's just slide. So for the sake of the test exam, don't use that the approach as shown in the slide, but that it doesn't mean it's not correct, but the process is correct. But the process is a lengthy process. We have the shortest way to solve this, so we use the shortest approach now. But again, before you solve the K matrix, we have 6 by 6. Then look straight away to your boundary condition first and eliminate the row and column, which is we do not need to use it in our problem. So for this 6 by 6 matrix, after we look at the boundary conditions, then our K matrix may be reduced into 2 by 2 only. All right, that's the approach. How should we use this document here? I have shared the documents in the e-learning since the first week of our meeting. So hopefully, I recommend you, because we don't have so much time to solve everything here. I recommend you to use this document and then try to work out on the same problem as in the lecture notes. We have 2 problems actually in the lecture notes here. So try with the simple one here, and then try to prove that you can get the same result for the K, and after that then solve for the unknown degree of freedom. So starting from the beam, you can start using your calculator in order to calculate or solve system of linear equations. So those who still don't know how to use calculator to solve system of linear equation, I recommend you to learn it quickly. Maybe you can ask your friend who already know how to use it, or maybe you can, now information is just at your fingertips. So you can randomly Google it, or maybe from the YouTube channel. Alright, siapa? Aiman, dekat e-learning tak ada. Ada dekat atas sekali, tak silap saya. Saya letak very top dalam folder, tak silapnya. Dekat atas sekali. Sekejap, saya pun boleh check sekejap. So, untuk hari ni, kita stop sampai sini je. But I strongly recommend you to apa ni?